Hello, I want to welcome you to Insulation Blowing 101, everything you need to know to do it right. My name is Jeff Wilcox. I work for the state of Vermont's weatherization program, and I'm a member of the Energy Out West board. Today we have two experts here to help guide you through the information. Bill Holstrunk, the Vice President of Insulation Technologies for Nature Tech Insulation, and Zach Green, the state of Vermont program monitor. Please sit back and enjoy the information, and if you have any questions, we'll provide our contact information. Thank you.
So we're going to start with a little bit of an overview on insulation machines. So all of the machines basically have these same kind of components. There's a hopper, which you're throwing your bag in there. Then inside the machine there's some sort of agitator, and that agitator basically is designed to do two things. The agitator breaks up the cellulose bale into smaller pieces, kind of fluffs it up a little bit. The other thing the agitator does is it helps to move the material toward the airlock. So in a little while we're going to look at one of the machines and look at the agitator tines in there, and if these things get bent out of where they're supposed to be, it's going to interfere with the distribution of the material in that airlock. So at the bottom of the hopper, then there is your feed gate, and this is used to control basically how much material is going to be dropping down into the airlock. And then below this is the airlock itself. So the airlock basically is basically a paddle wheel that is down inside this kind of circular drum down there. So when you pull the feed gate out, material drops down into the airlock. The airlock then rotates around, and when it rotates around, it's going to come to the point where on one side of this is your blower, basically a fan, and that's pushing air into the tube. And on the other side of the airlock basically is the outlet of the machine, and this is where you're hooking your hose on, and that's blowing material out. So those are kind of the primary components of your insulation machine, and we'll go and look at now a Crendel 1300, and we'll see kind of how those things are all work together. Okay, so a little bit more about that airlock. So what happens is on the end of the airlock, there basically is a shaft, and you have 6 paddles coming off of that. And on the end of these paddles is basically a rubber seal. So that rubber seal is what makes contact basically with the outside of the airlock drum. So as you use the machine, you start getting wear on these seals over time. And if you wear enough of the seals, what happens is the air from the blower coming in here now is going to bypass these seals and go by. So one way you know that the seals are getting bad in your machine is you start getting air basically coming out of the top of the hopper. So if you have material blowing out of the top of the hopper, that's an indication that you need to go and you should be testing your airlock and the seals, and we'll go ahead and show you how to do that. The other thing that can happen is if something else gets dropped into the hopper, you can actually bend these paddles, and when that happens, again, you're losing contact with that seal, and you're going to not have the same performance of the machine. If these paddles get too bent or the seals get worn out, what it means is that instead of the air going out of the end of the hose, it's coming out the top of your hopper, and it may get to a point where you're just not able to dense pack. And with our pressure testing, we're going to do some diagnostics on here where you're going to test the machine at the outlet, and then we're going to test the machine at the end of the hose and see if the performance, if the machine's running okay, and then we're going to get to see how the hose system is running as well. So we'll go ahead and take a look at those things.
So Bill, is that why you should never pick up material on the ground and put it back into the hopper?
Yes, so that was a good point, is if we're loading material into this hopper here and some material for some reason drops outside the hopper, unless it's a big chunk that you can actually take a look at and make sure that there's no nails or screws or things in it, So if you get something like that, you could probably put it back in, but we don't recommend actually sweeping besides the machine and dumping that in. You know, you're in the back of the truck, you're working out of the truck, there's fasteners, there's tools and things like that. What we find is there's a good likelihood, if you're sweeping stuff off the floor and putting it back in, that you're going to rip up that airlock very, very quickly. So, and if you were to take that cellulose, even though it looks like, you know, maybe a bit at the end of the job, and compress it back down to the density of the bag, even if there's a lot of material on the floor, rarely will that ever be bigger than like a size of a baseball or a softball. So don't think about, you know, we're losing some material, we got to put it back in here. It's better just because the repair of the airlocks will more than offset any material that you're ever going to use by many times. So that's a good point. Okay, so a couple of things with the blowing machine is if we look down into the hopper, we're going to see those tines in there, the agitator tines, and they need to be kind of bent like a propeller. So these should be straight, perpendicular with the agitator arms there, and they have kind of a 45-degree angle, and that angle is so that it can draw the material toward the airlock. It's a good idea to be checking the condition of these tines every couple months, because they do get bent up, sometimes severely, and again, if they get bent either so they're bent over, or you lose kind of that bend in them, all of a sudden now you have a lot of material on this side, hardly any material on that side. First of all, the hopper acts as if it's a lot smaller, and then it causes other problems, feed problems and production problems as you're moving through. So the agitator tines, it's important that we take a look at this. This machine also is a little different because it has a secondary box down in the conditioning box, which are those arms kind of down into the hopper there. The other thing is, over time you're going to get things kind of wrapped around the tine. So this one was just, we straightened the tines on this just a couple of weeks ago and removed a lot of the debris that was in here. So checking the tines, removing the plastic and things that gets wrapped around in here, that's important for the operation and the production of the machine. So a couple other things, just talk about some of the other maintenance on this machine here, is weekly. Some of the things you're going to be doing, or recommended from the machine manufacturer, is to take off. So on this machine, it has a blower box kind of on this side here. The other thing is the air intake coming into this machine. So the machine comes from the factory with just a short little pipe coming off of the air intake. Because it's located down kind of at the bottom of the machine, it's more likely to suck up material when you're loading the hopper. If something comes in here, it's gonna more likely to get sucked up in here. So in this particular case, they've taken the air intake and actually put it to the outside. I don't know if we can take a look at that. And what that means is it's going to keep that air filter a lot cleaner in there. So inside that box where that hose goes, there's a filter inside there and the blowers. So monthly we're going to want to take that apart. We're going to clean out the filter, and we're also going to clean out any material from the blowers. If that didn't go to the outside, then more likely on a more frequent basis, we're going to need to do that. Because it's taking it from the outside, it's going to generally keep that filter a lot cleaner. Okay, and then monthly, we're going to check the agitator tines. We're going to do a pressure test, which we're going to show you to do that. We're also going to inspect the chains, wipe them off, put some dry lubricant just to make sure that they're okay. And then, check the oil levels on the machine, clean the chains and sprockets, adjust the tension of on any of the chains. And then annually, we're going to want to change the gear oil on the speed reducer gear down in it. So those are kind of the maintenance things on the machines. It's pretty reasonable to go ahead and do that. Any weatherization agency can do that without any problems. So we're going to go ahead now and I'll show you how to do the pressure test off the side of the machine. So in order to prep for that, what we want to do is we want to close the airlock all the way. So on this machine, we can see that the airlock, or actually the feed gate is open. We're going to go ahead and close that all the way. So we're going to crank it closed. So we do this because we're going to want to make sure that no more material is falling down into the airlock when we're doing our pressure test, because it'll plug up our gauge and affect the test there. So we're going to go ahead and... Okay, so the gate now is fully closed. The next thing we're going to do is we're going to turn the air up all the way. And when we do our testing, our pressure test, we always, just for consistency, we're always going to set that blower control. So this is a dual blower machine, so we want to put each of the blowers at its maximum. And now we're ready to go ahead and test the output of the machine. So in order to do that, I got to pull off the outlet hose. Typically, we're going to remove all the material from the hopper before we do this. It just gives us the opportunity to go ahead and look at the airlock tines and to clear out any junk that's in there. So typically, we're going to do that. But you could do this pressure test with material in the hopper. It's just really important just to close that feed gate beforehand. Okay, so now that we've pulled the hose off the outlet of the machine, we're going to now blow the airlock out, and then we're going to go ahead and do a pressure test. So we're going to go ahead and turn the air and the feed on the machine just to blow the airlock out. Okay. All right. Good. Okay, so now we got our gauge here. We're going to go ahead and just press that over, and now we're looking for a minimum pressure of 2.9 psi or 80 inches water column. So we're looking at two things: how high the gauge goes, and then secondly, if there's any variation in the needle, if the needle is bouncing around a little bit. We're going to want to do both of those. If the bounce on the needle goes below that 2.9 or 80 inches water column, then we're going to need to do some repairs on the machine, because it's at that point we're not going to be able to dense pack effectively with the equipment. So here we go. We're going to put the pressure gauge on, hold it on there tightly. All right, that's good. So we got about 3.3 psi, and it's pretty stable. So that means it tests out well. So we're going to go ahead and we're going to put now the hose back on this, and we're going to now do another pressure test at the end of the hose. And if we don't have any leaks in the system, the pressure at the end of the hose will be the same as it is out of the outlet here. If we have leaks in the hose, bad hose connections, maybe the hose is worn out, you have holes in it, all of a sudden that's going to affect the gauge. And if this drops below, basically 1 psi between the outlet and the hoses, it means we have to take a look at our hoses and try to figure out where the air leaks are. So now we have the hose hooked back up to the machine, and what we're going to do now is we're going to pressure test now again at the end of the hose. So first of all, we're going to want to blow out any material that might be in the hose. So we're going to go ahead. I like using these grain bags because they let the air come out while they kind of catch the cellulose inside them. Let's go ahead and turn that on. Okay, it's all blown clear. Okay, so now we're going to go ahead and we're going to retest the pressure now, right at the end of the hose. All right. Okay. All right, so we got about 3.2 psi. So again, it's pretty close to where it was at the end of the machine. That means this hose setup is good. We got good, the hose itself doesn't have a lot of leaks in it. It's not worn out. And the hose connections are tight. So we're not getting any leakage. Again, it doesn't matter how good the machine is if you don't get that air pressure delivered at the end of the hose. And the reason why we do 2 tests is if we found a problem right at the edge of the end of the machine, we would know then that the problem lies inside the airlock or maybe a plugged filter if that pressure, overall pressure, were low. And then if we go ahead and hook our hose on and now see a difference between those two, then we know that the problem lies in our hose connections somewhere along, or the hose itself. Good. Let's talk a little bit about how we'd like to have our hoses set up on our machine. I find the best way to do that is coming off the machine, we're going to have 2 50-foot lengths of 3-inch hose. So that's the hose we're going to use whenever we go up into the attic. Because we want to not restrict the material flow, we want to deliver it as fast as we can. We're going to be blowing right out of that 3-inch hose. If we neck that down and go to a smaller hose there, what we're going to do is as we decrease the size of the hose, we increase the velocity coming out at the end of the hose. So therefore, in an attic, if we're blowing with a smaller size hose, it's going to be a lot more dusty. And our production levels are really going to be reduced, and I'll talk about that in a little bit. So again, at 100 feet of 3-inch hose, then we're going to go with a 3 to 2 reducer, which is a double stepped.
So Bill, you're saying when you open blow 3-inch hose, not a 2, the 2 is going to have more velocity, more dust.
Yes. Yeah. So with that 3-inch hose, we're going to be using that in the attic. We don't want to reduce that size in the attic because we're going to increase the velocity and increase the dustiness of it. And we're going to reduce our production significantly by doing that. So off of our 300 feet of 3-inch hose, we're going to have a 3 to 2 reducer, so it's a double step down. This 3-inch hose will go here, your 2-inch hose is going to come over here, and then we're going to have 50 feet of 2-inch hose, which is this size here, coming off of that. So this will be, we'll put this coupler in there anytime we're dense packing. So therefore, if we're changing from open blow to a dense pack, the only thing we have to do is loosen up our hose clamp and pull this out. I like hose clamps a lot more than duct tape because they're more secure, less likely to come undone, and unfortunately too many times we've had the hose kind of blow out in the middle of somebody's house, and then you end up with a lot of extra cleaning to do on that. So at the end of our 50-foot section of hose, what I'm going to do is I'm going to cut about a foot off the end of that 2-inch hose, and I'm going to mount one of these Intech 2-inch swivels in here. And this is nice because now when I'm dense packing, I can turn this whole thing without having to turn the entire hose. It makes a lot of sense. And I'm going to have our dense pack hoses all set up so they're all going to be able to plug into this 2-inch hose. Again, hose clamp here. So on our trucks, we're going to want to have 3 different size hoses. We're going to want to have a 1.25 inch, 1.5 inch, and a 2-inch hose. So those bigger cavities in the attics where you have rafters coming down, if we can get that 2-inch hose in there, we're going to do that because the hose size really makes a big difference in terms of our production. I have a little chart here. I think we're going to superimpose this on. So if we go from our 1.25 inch hose and we go up to 1.5 inches, all of a sudden now we're going to have 50% more area, so therefore it translates into 50% more material moving through the hose at any time. And if we go from our 1.25 inch hose up to 2 inches, all of a sudden now we're over 2.5 times faster that we're going to be able to put the material in. So in general, we're going to want to use the biggest hose that'll kind of fit into the cavity. The reason why we have 3 hoses here are that there are some walls, 2x4 walls, maybe a back plastered wall or something like that, where the big hoses just won't be able to fit in. I'm going to show you some techniques of how to drill some holes that allow you to easier use some of the little bit bigger hose maybe than you're accustomed to using. So the other thing we want to do when we're evaluating kind of these hose connections is I see this one a lot of times. So this is, a lot of folks think that this is kind of the universal hose adapter where they can plug any size hose in here. But the problem with that is, so here's an 1.5 inch hose, and if I plug this thing in, we're now looking at kind of, you're restricted by your smallest area. So if we look at that smallest area there, all of a sudden now this 1.5 inch is acting like a 3/4 inch hose. And if we go back to our chart here, we can see that 3/4 inch hose. So we're reducing our production over what this hose is capable of by a factor of 3 or 4 times at that point. So we're and we're going to be a lot more prone to clogging up. This is going to clog up a lot quicker than this. So what we're going to do is we're going to now put a better adapter on the end of this hose. And the adapter I like using on this 1.5 inch is actually a straight 2-inch adapter. So this will actually go over the outside of this. Now, before we do that, we're going to want to basically prep this hose. And if we do an outside connection, so the outside connection is important because we don't want to reduce the inside area of that hose more than we have to. So basically what we're going to do is we're going to bevel this inside edge. Basically we're creating kind of like a funnel. It's not going to restrict the material. There's nothing for the material to kind of bump into and kind of clog up. So after we get our bevel there, we're going to go ahead and put a little tape on this because we're going to want to make a nice snug fit on it. So a couple wraps of tape on the end of this. We don't want the tape to go beyond the outside edge there. Okay, so now we're going to slide this on. We'd like a kind of a snug fit there, so a little bit more tape on that. Okay, so now we got a nice snug fit on that. If we're using one with a reducer on it, on a smaller hose, we want to make sure that we're not pushing this past that smaller end of the hose there where it could create something to kind of get jammed up against. And then we're going to go ahead and we're just going to tape that now on the end of the hose. Some tape. This way, again, we're not restricting the inside diameter of that hose, so therefore we're going to get the maximum productivity, and it's going to, again, reduce the chance that we're going to get a clog in that. And when we're done, we're going to have a nice smooth fit here. Again, 2-inch, it'll plug right in there. We can quickly change that over, and we'll get that. So we can use this 2-inch coupler actually on both the 1.5 inch and the 2-inch. So the 2-inch, this will actually slide right up inside that, and that actually is such a tight fit there that a lot of times you don't even need to tape that. The 1.25 hose, we can either use a reducer like this. Again, we don't want it to neck down to a really small diameter, but this one has a thin wall, and it basically just barely fits in the side of that, and so that's a pretty good way to do that. There is another one, coupler, that I use that fits on the outside of this. Maybe I'll give you a quick show of that one. So these are pretty much a standard adapters from your local auto parts store. So this one is 1 inch and 7/8 inside, and 1 3/4 inch outside. So on this one, again, I can take this off, bevel that edge, slide this over, and go ahead and tape that on. And this is the size now that'll fit right into that. And again, these are just 2-inch outside diameter straight couplers, and we're going to use those on the other two hoses.
What are the benefits of using the largest hose possible up in a hot attic?
Yeah, so one of the reasons why we're interested in productivity is not only just kind of shorten time we're on the job site overall, but it's also shorten the time we're up in that 130-degree attic or underneath that mobile home when, in the winter time when the temperature is, 10 degrees. And the larger the hose, the less chance you are of plugging the hose and having to deal with issues where you're constantly unplugging. So the bigger hoses just make your life a lot easier out in the field. So kind of think of that is, let's try to use the largest size we can for the particular cavity that we're insulating. All right, I just want to talk briefly about storing hoses in the truck. We'll go ahead and do that. So the other thing that I found is a couple of things. We talked about hoses. One thing that I want to talk about is where you cut your bevel on the hose. And I'll give you my thoughts on that. So these hoses kind of have this natural curl to them when they're extruded. And when we're cutting our bevel, so the reason why we cut our bevel at the end of the hose is if we cut the hose flat and we push our hose in, we could be pushing that right up to something tight, and if we start blowing at that point, we could instantly plug the hose. If we cut it at a bevel, it gives us more ability for that not to happen, and it gives us some directionality. Again, remember that swivel that we put on there. If this is in a wall system or a floor system, and we turn this hose, that bevel actually allows us to basically directionalize or make the cellulose come out in different areas there. And the bevel, the way I like to put it in is this hose has a kind of a curve this way. If we cut our bevel this way, now when I'm pushing that hose along the cavity, maybe up into a wall or along a floor system, it's going to ride up on that bevel and it's not going to get stuck or jammed up as much. If we cut the bevel in the opposite direction, so this actually, the bevel this way makes it easier to get this hose initially into the wall. So that's why it's cut this way a lot of times. Again, if we change the way that we're drilling our hoses, we don't need to do that. But what I find is when it's this way, if this is rough, plaster and lath and things like that, this end could be catching on things, and sometimes it just makes it more difficult to kind of push into that cavity. Also, it's important that we store these hoses in a manner that is straight. If this hose is curled up, when we're working with it, we're basically struggling all day trying to get around that curve. So what we want to do typically is in our truck mount a piece of 4-inch waste and drain pipe that we're sliding these hoses up in, or we have an area of a truck where it has the ability to slide these hoses and keep them straight. So the straighter the hose is when you pull it out, the easier it is going to be to work with. Okay, we're going to talk a little bit more about hose prep. So a couple things that I like to have on my hoses to make things a little bit easier. One is I want to mark kind of the end of the hose, where the end of the hose is, about a foot back. I like to put kind of 2 marks there. That way when we're pulling it out, we're going to know that the end of the hose is coming up. Instead of pulling it out and all of a sudden getting a face full of insulation, we're going to know the end is there, so we can go ahead and now turn the machine off as we get a little bit closer. The other thing is I like to actually mark on my hose in foot increments, because this allows me now when I'm up into a wall and I'm hitting something where now I might, so if I'm putting it up and hitting something here, I'm going to know, well, I got a blocker 3 feet up. And so unless I can twist that by, I'm going to now need to put another hole up there so I can mark it very quickly and kind of use it as a measuring device without looking for my tape measure and trying to figure out where that is. So on this hose here, we're going to go ahead and just put some marks on the end of the hose. About a foot back. Okay, and Zach's gonna insulate this test box. So we're going to start with the 1.25 inch hose, and we're going to time it, and then we're going to reset the machine for an equivalent density, and then insulate it with that 1.5 inch. So there'll be a 1/4 inch difference between the hose size, and we're going to go ahead and see what kind of difference that makes in terms of filling up a cavity. Okay.
So Bill, how often should a crew use the test box, and what's the purpose?
Yeah, so the test box is important for a number of things. When you get a new machine, it's good to do a test box because you can get your settings kind of dialed in at that point. And I do recommend that when you do that, maybe even write those settings right on the machine. So if for some reason you have the machine being used by a different crew, they can quickly be able to see, okay, here's the air setting and here's the feed setting in order to make sure that they're getting the proper densities. So as we go and change the different hose sizes, we're going to actually change the settings on the machine to give us the equivalent densities. So the larger the hose, the less friction that we have, and the more we're going to be able to open that feed gate and get the same density. So that's how we actually get more production out of these larger hoses. And you know, sometimes really, you know, a smaller hose, maybe an inch hose there, is not bad to have on the truck, just in case we get into a wall where we basically have what we call a double plastered wall, where there's a plastered wall inside the other wall that we see in some houses, and it leaves us now with a very, very small cavity. So we're going to might need something smaller than this in order to get in there. But that's the only time I really want to use those smaller hoses, is when we're physically unable to get this 1.25 inch in. Then we'd maybe go to one of those smaller ones. So we'll go ahead and go ahead and insulate this test box.
Okay. Someone want to time me?
Yes. Ready? Okay, so go ahead and start the timer here as the material is coming out of the end of the hose. It's good to have a test box with a clear front on it, because it helps illustrate to the folks that are insulating how the cellulose actually is going in there. And a lot of folks find it's kind of interesting that the material comes out of the end of the hose and then basically starts packing up in there. And only once it basically is packed up in there does it now start to, you'll see it as Zach pulls that out, it'll start to compress now the cellulose going in there. And you can see as this is coming up, it's basically building that density. And again, that density is important because it's an enclosed, whenever we're blowing into an enclosed cavity, we have to dense pack. And so that dense pack in there makes sure that we're getting the density correct so that it will never settle inside that cavity. And we'll do a little demonstration afterwards, after we blow a wall over there, to show you that truly the material is self-supporting. So over time it cannot settle because it's basically exerting enough force at the edges of both the edges of that bay that it's in. Okay, we can see how that cellulose, as it flows out, it basically is in every nook and cranny inside that box. And that's why cellulose is so effective at blocking air leakage, because basically those fibers get everywhere, and the density of the material is so attenuating, airflow attenuating, that we're going to improve the air leakage of the box. Okay, so that is looks like 2 minutes inside there. So now we're going to shift to the 1.5 inch hose and go ahead and do another run on the test box. Okay, so if we had blown that test box and found that the density was not high enough and we needed to make an adjustment, then we have to figure out what we're going to do with the machine in order to do that. So if we're using a single blower machine, so most of these single blower machines, we have the air all the way at 100% all the time. Whether we're up in an attic or whether we're dense packing, we're using, basically, we're always at 100%. If we have a dual blower or multiple blower machine, like we do with this Crendel, then the issue is sometimes we got so much air volume that you're going to start to be blowing stuff apart. So in that case, maybe we're going to turn down those blowers a little bit. And then in this machine, we do have them turned down a little bit to make sure we don't blow things apart. So in terms of the settings now, in order to increase the density, I kind of think of it this way, is the more that feed gate is open, the more material is going to fall down into the airlock, the harder time that air is going to have pushing now that greater amount of material, and the less dense it's going to be at the end of the hose. And you know, if we reduce that feed gate, the less material goes through, the air has a easier time pushing it, and it's going to be able to pack it at a higher density. So if we want to increase the density, our density at the end of the hose there, or in our wall or floor system, we're going to now reduce then that feed gate a little bit more. But since we were right on the mark here with the settings on the machine to give us 3.5, we're going to go ahead now, we're going to switch the hoses to an 1.5-inch hose instead, and we're going to repeat this test, and we're going to now see, we're going to retime it and see if now we've get the same density in the box, but now have reduced our time a little bit. So we're going to go ahead and do that. Okay, so here we are now with the 1.5-inch hose. We're going to go ahead and blow the box again. Again, the first one was 1.25 inches. It took about 2 minutes. So we're going to now see how long it takes to put that equivalent density in that box with the 1.5 inches. So go ahead. Ready? We can see with that larger hose how much quicker the box starts to fill up. Just much more efficient at delivering that material through there. And again, the bigger the hose means less friction, so we can actually open up that feed gate a little bit more to give us that equivalent density. Okay, just a hair over a minute. So that 1/4 inch difference in that hose size has basically reduced our time by about half. So we're going to go ahead and weigh the box just to make sure we get the equivalent density. But okay, got our scale here. Okay, it looks like 42.5 and 42.3 is 3.5, so we're a little bit higher density than the first one, and we've reduced our time to insulate that same cavity by about half. So that's a pretty good trade-off. And again, the larger hose means less opportunity, less chance for clogging, less headaches in my mind. So next, what we're going to do is we're going to show you how to maybe some other ways of drilling some holes to allow you to more easily kind of get that larger hose in the cavity. So in terms of drills and bits, again, we want a drill that's going to have enough torque to be able to push this through the wall. I prefer one with a clutch on it. So DeWalt makes now one of these that's a little bit shorter that has an electronic clutch on it. And that's nice if you're up on a ladder and you're drilling and the bit gets hung up. All of a sudden now the clutch means that this thing isn't swinging around, smacking you in the head, knocking your teeth out. throwing you off the ladder. So those work out well. You know, DeWalt makes some. Milwaukee also has a similar one. And in terms of the bits, these are pretty much the 3 bits that I see most often out there. So first of all is a hole saw bit. The problem with the hole saw bit is it's slow to kind of drill through the wall, and then you're left with now a plug in there that you have to unplug. Now these Diablo quick change bits make it a little bit easier, where you take that off and now you can push that plug out. But if you're up on a ladder, sometimes that's not very convenient, and you risk either falling off the ladder or your tools falling off the ladder. The bits that we had been using a lot in weatherization prior to this other bit here, this is a cell feed bit. So this basically has a screw on the front, and this helps pull the bit through the wood. So it's removing literally all of that wood is coming out. The nice thing is there's no plug that you have to pull out of it. And actually Milwaukee has now one called the Switchblade, which has a replaceable cutter. So when you're drilling in and you hit a nail, which inevitably you're going to hit, the Switchblade allows you now to pull out the pilot bit and now replace it with a new sharp bit. On these, what I recommend is if you're using these kind of bits, you carry a diamond file inside the vehicle, inside your truck, so that you can now keep these things nice and sharp. There's nothing worse than a dull bit. The bits that kind of I find are even a little nicer are these, which is a kind of like a hole saw, but it has, so this one has 3 teeth on it, and these teeth are larger, which means that when I'm done drilling through the wall, I can literally just take the drill and drop it down, and usually the plug will just fall right out of it, which is really helpful and convenient when you're up on a ladder or something like that. So 3 teeth on this thing. Again, with a diamond file, we can kind of keep these things nice and sharp. These things are lightning fast compared to either of these other 2 bits. Now, the one thing we have to remember, kind of get a little used to on this, is it's so fast that if you're used to these other bits, sometimes you're going to tend to want to plunge this into the wall. And if you plunge it into the wall where there's wire, you're going to tend to get tangled up. But this is all of just getting a little used to your bit. You know, when you're getting close to it, you slow down a little bit and just avoid basically that plunging coming in. And this bit basically, so if I'm going through drywall, then I'm going to use a hole saw. But pretty much anything else, I'm going to try using this bit. Sometimes with some delicate plaster and lath, maybe you're going to need to go back to your hole saw, but for pretty much anything else, this bit works well. And Zach's going to now show us on this wall a couple different ways we can drill to make it easier sometimes, to make it easier for these larger size hoses, because that's some of the problems we're having is it's difficult to get the hose in. How we drill those holes a lot of times makes a lot of difference. So before we go ahead and drill on the outside of the house, we're going to want to go on the inside. And usually we prefer the person that's blowing be the person that's inspecting the inside. So therefore, if there's a hole or something, they're the ones responsible for not catching that. So we're going to look inside kind of where the level of our outlets are, because electrically, when we're wiring the house, we're going to run those wires typically, you know, at about the same level as the outlet. So we'd like to be either above or below that. In terms of ergonomics, in terms of working all day long, we find that it's most comfortable to kind of be working between our waist and our chest. If we're working real down low or really up high, by the end of the day, we're going to really feel it in our back. So we'd like to be kind of working in that level when we're doing that. So go ahead. Zach now is going to drill a variety of holes. So the first one is just going to be a straight hole using the 2 9/16 inch bit. So the nice thing about the advantage of the straight hole going in is we can use now a wood plug to go ahead and plug that hole pretty quick, pretty easily. Okay. Okay, notice how the plug ejected out very easily from that. The next hole that we're going to be drilling is again with that 2 9/16 inch bit, but now we're going to be basically we're going to bevel that hole both up and down. So we're going to go ahead and start drilling it at an angle, and when we're done, we're going to bevel it the other way, and that'll just allow that hose to be able to slide in easier. This is particularly helpful if you have multiple layers of siding or some really thick siding on the building, which sometimes can interfere with the ease at which we're going to get that hose in. That beveling sometimes can make all the difference on that. So the beveled hole is going to be harder to find a wood plug that's going to fit in there. So when we're beveling the hole, or when we're doing the next one, which is the figure 8, we're going to basically be using our foam gun, foaming, pushing the cellulose in, foaming it, letting it dry, and we're just going to come back and clip it flush with the outside. Okay, so now we have a beveled hole on that one. Our next one, we're going to do what we call a figure 8. And the nice thing about the figure 8 is it allows us to use still that smaller bit. And we're going to get now an even easier way to kind of slide in the hoses there. Typically, when we're doing a 2x4 wall, if it doesn't have any insulation in it, or a 2x6 wall with a kind of a thinner bat in there, we're going to try to be using that 1.5-inch hose. Because again, we found that when we use that 1.5-inch hose, we basically reduce our installation time by about half when we're blowing. The other nice thing about that bit is, unlike the self-feed bit, we're not actually removing all of that wood at once. So we're just basically cutting out this thin little layer here, and that means that there's less torque on this. It means less chance of this thing grabbing and smacking you, and it just makes things a lot easier when we're dealing with a bit like that. There we go.
Thank you.
Yep. Excellent. Okay, as we can see, now we got a slot here. That hose is we'll go ahead and try the hoses after, but we'll find it a lot easier to get it into that one. And so the third one is we're gonna step up from the 2 9/16 inch, and we're gonna go up to a 3-inch. Again, we're gonna grab the 3-inch here. So larger hole size means, again, we're going to have an easier time getting the little bit larger hose into that cavity. Okay, so notice also, so Zach is probing now left and right with the probe to figure out where he's going to find the framing in here, and therefore where he needs to drill that next hole. We're going to actually use the hose as our up and down probe. So between kind of the side-to-side probing and using the hose up and down, that'll make sure that we get the entire wall insulated, and we're not going to leave any bays or any voids in that wall system. So the reason why we're cutting the building paper here instead of just drilling right through it is, when we're done, we're actually going to put these things back, and it's going to help to make sure that no water is going to now get into our wall system. So again, with this, if we drill straight in, we'll be able to use now a 3-inch or close to that wood plug in order to plug this. So plugging will be easy with that straight drilling. Okay. And Zach's now going to get the hose, and he's going to kind of show how easy it is to feed that 1.5 inch hose into each of these holes here. So again, the first one's just going to be the straight 2 9/16 inch hole. Again, the hose will fit in through this 1/2 inch sheathing here. Okay, great. All right, see, he measured now with the hose there and was able to determine that there's no blocking. He would do the same thing now when he's insulating the, insulating the bottom of that cavity. Okay, this is one with the beveled edge. Notice how much easier it was to fit that hose in. So now he's going to do this next one here, no blocker on it. He's going to do this with just one hand. He's going to show you how much easier this is. Literally the hose just slides right in there without any difficulty. Again, measured it out. And now we're on the 3-inch hole. It's a little bit bigger one there. Again, you can see how much difference a larger size hole or adjusting our drilling is going to make in terms of your struggle of getting that hole in there, that hose in there. Now we can also, if we run into problems getting the hose in there, we could use something like this. So this is what we've deemed the hose horn. So basically this is a electrical PVC sweep. If we get one for this hose, we're going to want to get a 2-inch, cut a 2-inch electrical PVC sweep into kind of like a shoehorn. And so what we're going to do is put that on our wrist here. So we can use this to kind of help us, particularly if we have that back plastered wall, just to get kind of the hose started, and then afterwards we can get it in easier. So if we have a back plastered wall where we have an interior layer of plaster, this can help us to get beyond that first cavity into maybe that larger one if it's on the inside. So these things are all things you could use just to make your life a lot easier out in the field. Okay, so let's talk a little bit about why we're using this single hole method over a 2-hole method over, maybe a single hole using a nozzle. Let's talk about all of those things. So let's draw kind of our wall here. Okay, we have some wall studs here. Okay, so in the old days, we would use what we would call a 2-hole method, where we'd be drilling a little hole, 2 little holes, and we'd be using typically either a short straight nozzle or a directional nozzle, and we would put it in here and insulate the wall. The disadvantage of doing that is we have to remember that as soon as the cellulose leaves our hose or nozzle or whatever we're using, the velocity starts to drop, and therefore the density starts to drop off. So when we were using this method, what would happen is you get really good density around the hole, but the further away from the hole you got, the less density you had. So when you were done with this, again, you'd push your hand in the hole, it would feel like you had pretty good density, but between these holes, the density would drop off, so that between these 2 holes, the density typically fell below that self-supporting density. So over time, what would happen is this would settle, and now we'd get a void at the top of the cavity. It might not happen, that void typically wouldn't happen right away, but in the next couple of weeks to months, that would develop. So we've gone away from that. So the same thing with the nozzle. So if we use a nozzle and try to do that with let's say 1 hole hitting here with a nozzle, the same thing's going to happen. We're going to get really good density right around that nozzle, but beyond that, the density is going to start to drop off, and over time, this is going to be very, very prone to settling. In order to compensate for that, you'd need to drastically increase the density at which it's going in, and now you risk increasing it so much that we surpass the mechanical limit of this wall system, and now all of a sudden we start blowing things apart or levering things apart. So this is why we've developed basically this single hole tube insertion method, where now we're going to drill a single hole in here, and now we're going to take our hose, We're going to put it down to the bottom of the cavity. We're going to fill now up to the hole, and now we're going to take the hose and we're going to now put it up to the top and now insulate down. Again, we're going to use the whole hose to make sure that we don't have any voids or gaps or any blocking or anything in here that we got to drill another hole for. And when we're done with this, we're going to have now consistent density from the top to the bottom. So we can put this in at 3.5 pounds per cubic foot, and it's going to be truly self-supporting. So over time, there will be no settling or sagging going on in there. So Zach's going to go ahead and do this. I prefer actually myself to actually put the hose down at the bottom first. And the reason for that is, as we saw with the test box, when the hose is down there, there'll be some material that comes up above the hole, but it'll be fairly light. So light that we're going to be able to now push that hose up through this material without any problem, and we'll be able to get it all the way up to the top to make sure there's no blocking there, and then we're going to go ahead and insulate back down to the hole. So we'll go ahead and give that a shot. So he's actually going to bump the bottom of that cavity, and that way he knows that he's gotten all the way down below. And again, by looking now on the hose, he's going to be able to see how many feet the hose is in there, and be able to determine if we have to drill another hole or not.
We're at 4 feet. I see
4
the
feet.
seam of the plywood.
Yeah.
The plywood's 4 feet, so I know we're
Great.
good.
Excellent. And sometimes you get cellulose blowing kind of between the studs, and we typically will take a little bit of fiberglass and maybe just stuff it in the next couple holes, just so you have less material coming onto the ground. It means less cleanup, just to make things a little bit easier, better. So he's using kind of an onion type bag around the hose there, and it's doing a good job of containing the material in there. Plus it's nice because it's not going to fall apart like a piece of fiberglass is going to. Okay, so we turn just the air, sometimes just turning that air on also can allow the hose basically to blow the material out of the way. And particularly if you have a fiberglass bat in there, it might help actually quite a bit being able to get that hose into a bay that has some existing fiberglass in there. Okay, great. Okay, he's just touching up the end of that hose just with the air only, because when the feed is on, then it's pushing more material through the hole or the hose. Also, that avoids this kind of weak area here. If you're looking at the wall with a infrared camera after you're done, if you don't make sure that, if you leave kind of a divot here, that'll be apparent in the the infrared, and that'll be kind of a weak area there. So getting the hole filled all the way right up to the edge here is an important factor. Okay, so now we're on to that second one, which was that beveled 2 9/16 inch. A little bit easier. You can see how much of a struggle it was actually on that straight 2 9/16 inch. That'll wear you out by the end of the day. Just a little bit of extra effort compounded by, you know, dozens and dozens of holes means that you're going to be that much more tired. Now the other thing that's important is we have an understanding of how many bags of cellulose should be coming in here. This is going to do a couple things. It's going to tell us whether we have blockers in there and we missed some areas if their bag count is off. It's going to tell us maybe that our densities are off and we're going to need to make an adjustment on there. So the bag count is important. So there's a couple of ways we could kind of do this. So in a standard 2x4 wall, each bag of cellulose should go about two bays. So whoever's loading the hopper, good communication there can get us kind of dialed in terms of that. The next thing is a bag count for the entire job. If we have an empty wall, let's say a 2x4 wall, and we know kind of the square footage of that wall system, we can now calculate how many bags are going into that wall. So that's kind of that extra check. If the end, you know, if we figured that this job should be doing 50 bags into our exterior walls, and at the end of the job we say, well, how many bags did we use? We used, you know, 52 bags. We then know that we didn't miss anything and that our densities are correct. So it's kind of that check, particularly when we're doing unvented roof assemblies. If we're tubing down and insulating a sloped ceiling, that bag count is really important because density in an unvented roof assembly is that much more critical because we need that cellulose to be right up against the exterior roof sheathing there in order to protect it. And we don't want any kind of gap in there. So density is really, really critical when we're doing it. So whenever we're doing an unvented roof assembly, we're going to make sure that we do a bag count on it. But it's a good technique also applied to everything else. It also helps the crew. If we know that they're using about 50 bags on this particular job, they know how many bags they're going to need to put into the truck. Instead of saying, well, we're always going to fill the truck up, put as many as we need, you know, that's a hassle because then you're moving sometimes bags in and out of the truck. I always do, you know, if we're doing an attic open blow, always put definitely some extra bags. Just, you know, the more confined that attic is, maybe the less we're going to have to increase the density a little bit because we're not going to be able to optimize that. So in an attic open blow, just to go a little side thing here, the bag coverage charts are determined by holding that hose at a 45-degree angle and shooting that material up and having it land about 10 feet in front of you. Now that's great if you're in a big attic or in a big open space at which they test the density and determine the bag coverage charts. But we know that a lot of the attics that we're in are confined. You know, there are some attics where literally we're crawling in on our belly to insulate that. We're not going to be able to optimize that hose angle, so therefore the cellulose is going to be going in at a higher density, and that reflects back to I'm going to have more bags on the vehicle. So the attic size actually is going to mean that we're going to need, the more confined the attic is, the more bags we're going to have to be put in there in order to kind of compensate for that lack of the ability of holding that hose up. But here we are in
Bill, how do you do the bag count? Like, how should the crew do it? After a quarter, or know how much?
Yes, well, that's a good point. So it would be good to, after we do a couple of these bays, to basically find out. So we're going to start with the machine, you know, typically, you know, pretty full, and then we're going to count the number of bags that we put in after that. And after we've done a couple of these bays, we're going to now fill the hopper up to its original level, and that way we're going to be able to figure out how many bags. And then on an entire job, we're basically going to be keeping those bags and keeping track of it. And in a lot of the trucks, you actually see a bunch of pencil marks there where each time they put a new bag in, they're marking it on there, and at the end of the job, they can just count up the ticks in there to be able to determine how many they've done. So the nice thing about cellulose is, let's say the bag count was off. We're supposed to use 50 bags on this particular job, and we only use 35. So that immediately is an indication that we did not get the correct density. The nice thing about cellulose is when the density is not up to where it should be, we can now push the hose back through it. And again, typically what we're going to be doing, like Zach did, turn the air on, it'll help to kind of blow that up, and that tube will go back in. Once it's dense packed to 3.5, 4 pounds per cubic foot, we're not going to be able to reinsert the hose. So this is the other way of basically testing the density, the person at the end of the hose being able to test the density to see if it's self-supporting, to see if it's okay. That trying to push that hose back in is really important, particularly when you're up in an attic and things like that and doing a roof slope where that density is really critical. But here we are on to the next hole. It's a little bit easier because now this next one was beveled. The hose went in a little bit easier. And
just one more thing, Bill. You've talked a lot about pressure and density. Depending on your hose size, how close should you be to the top or bottom of a cavity that you're dense packing?
That's a great point. So as we increase that hose size, we're reducing the velocity out the end of the hose, and therefore we're going to, in a very wide cavity, let's say we're going down a roof slope where we have 24-inch on center, with these bigger hoses, the speed at which we're putting the material in is going to be a lot faster, but we're not going to get the same density across that cavity. So with that 1.25 hose, we're going to get about 18 inches from the end of that hose. We'll dense pack from the end of the hose. We go to 1.5 inches, that distance reduces to about 1 foot. And then on that 2-inch hose, now we're about we'll dense pack about 6 inches from the hose. So in the really big cavities, what we'll do is we'll always use the initial big hose in there, and we're going to actually pre-fill the hose, pre-fill the cavity. So we'll open it, the feed gate up that much more, sometimes 2/3 of the way, be able to dump material in very quickly with that large hose, and then now we're going to reset it and then go back with a smaller hose in order to firm up that density. So again, in an attic, we'll just diagram this maybe to make it a little bit easier to understand. Okay, so here we are up in an attic. We got our rafters coming down through here. Again, if we have 24 inches between these two things, and again, because these are larger cavities typically, 2x8s or greater, a lot of times we'll be taking that 2-inch hose and we'll be putting it in on each side. So go ahead and, if we do 2 runs through here, we got to remember we're only going to get 6 inches from here and 6 inches from there. So that's going to leave, a little bit less than a foot between these two. That's enough of a density drop off where we're going to want to try to then retube this again with that 2-inch. Now the thought is, oh man, you're going so many times through here. But even if they were using that 1.25 hose, we would want to be sending that, usually at least 2 times through here. So this is an extra time we're putting it down, but because we're using that 2-inch instead of that 1.25 inches, it means we're getting, 3 to 4 times, 3 or 4 times the speed on it. It actually will be less time doing this than it would be to try to insulate it with that smaller hose, even just with those 2. So we're going to want to, kind of remember to do that, and that's a great thing to remember, that's the downside of the larger hose, that we're not getting as dense packing as far away from the hose, but we're going to more than make up for it because the hose is just so much faster than the smaller one. Now when we're insulating, we're also listening. The installer has a number of ways to make sure that material is coming through. Now, if for some reason the installer wasn't paying attention and material had stopped up in this hose and wasn't coming out of the end of the hose, it's not going to take long before that hose gets plugged up. And the one thing that just drives people crazy is constantly having to unplug hoses. So the installer is making sure that whenever the feed is on the remote control, that material is actually coming out of the end of that hose. He's also listening in for other things. You know, a lot of times when you hear that kind of noise in a cavity, that's time to turn off the machine and go inside to see if maybe you've blown off a piece of sheetrock or some other interior, wood paneling or something like that. On certain of these walls, we're going to have a hard time blowing. So wood paneling, 3/8 inch sheetrock, plaster and lath that's really delaminated. Those are all things that are going to be difficult to blow behind. So in order to be able to do that, we're going to typically have somebody on the inside of the building with a 2-inch piece of rigid insulation board holding it in place basically where they're blowing. Once the cavity's blown, you can take that off and it won't continue to press or exert any force to that. So that way we're going to basically temporarily blow it, be able to blow it, where if we didn't have somebody on the inside, we're going to dislodge that material on the paneling or whatever on the inside, and we're going to create a big mess in there. So we'd like not to do that. Now on our inspection inside the house before we start blowing, we're going to be crawling in the back of these closets and things. And a lot of times, it seems like, oh, this is a pain in the neck to crawl in back. But the question you have to ask yourself is, if there's a hole back there and I don't see it and it fills up the closet, would I rather go in the closet now and look for the hole, or afterwards and now have a lot of cleanup to do with the cellulose? Unfortunately, I've been on job sites where we've literally, filled a walk-in closet full of cellulose where you open up the door and it's all the way to the top. That's going to take a long time to clean up, and the customer, the client, is probably not going to be too happy that, you've now dense packed all their clothes inside the closet. Okay, so that was at 2 9/16 inch beveled hole. Was that a little bit easier than that first one?
A little bit.
Okay, great.
But not a whole lot.
Not a whole lot. All right, so now we come to that figure 8. And again, hose just slides right in there really quickly. Now, as much as you say, well, it's going to take longer to patch that hole, it will, but the ease at which the hose goes in is just more going to offset that overall. Okay. Also, let's talk a little bit about if you have a problem where something blows apart. So if you've blown a wall out or something like that and you go back and look at it, what you should be looking at is 2 things. When sheetrock maybe is pushed back, when the sheetrock is pulled back, what is the density of the material behind there? If it's rock hard, that means it's a density issue, and maybe we have our machine set up so it's just basically has levered that apart with that density. So in that case, again, it's too dense maybe. Maybe we're putting it at 5 pounds per cubic foot. Now we're going to open up that feed gate more to lower the density to get it back more to that 3.5. Or if we now pull that sheetrock off and we find, that's weird, the material behind there looks really fluffy, that means it's an air issue. We've introduced too much air volume into that cavity, so it was not able to basically have enough air relief to let that air out, and we've basically inflated that cavity and caused something to blow apart. So in that particular case, we're going to then need to either brace it from the inside, or we're going to need to reduce our air setting. And so if we reduce our air setting, we're going to have to reduce now our feed gate setting to to maintain our equivalent density, and that's going to take, we have to remember that is going to take longer. Okay, great. And how was insulating, getting the hose into that wall?
That was very easy. I was able to not shut the machine off. And
Oh, okay, great. And that's another, it's going to save a little bit more time with that as well. Okay, great. So now this last one is that 3-inch hole that we drilled. Go ahead and so that 3-inch hole sometimes is a little bit more like that beveled 2 9/16 inch. So again, if you're using wood plugs and you just want to make it easier to get the hose in, maybe that 3-inch hole can make sense. And if not, that figure 8 really just makes a whole lot of, can make a whole lot of sense in a lot of jobs. Talk a little bit about personal protection with cellulose. Cellulose is considered a nuisance dust. Just a standard dust mask is enough to protect you. You don't need to have any other protective gear on. It's a good idea if you're up in an attic. You always want to be wearing a dust mask. That's going to keep you from inhaling the dust. Any dust, enough of it is not good for you. So that would be a good thing to do. Outside, it's also good just because you're so close to the hose that sometimes you get stuff blowing out of it. It just makes a whole lot of sense to do that. And you could tell that Zach has done this a lot because there isn't big piles of cellulose on the ground. He's kept that ground pretty quick. It's going to be really easy to clean up after that. And again, using that big hog bit that we talked about, the one with the 3 teeth on that, it means you're going to have less chips to clean up than if you were using that self-feed bit, which basically is turning that whole hole into a bunch of little wood shavings. So that's the other advantage of it, and it's going to be easy to pick up the holes from that other bit as well. So after we're finished insulating this one, what we're going to do next is we're going to take off the back of the cavity. So now we can see basically how we did in terms of make sure we didn't miss any bays, and again to make sure that the material is self-supporting. We did a test box beforehand, so we know that thing should be really dialed in terms of that. Okay, great. Okay, excellent. So again, on this one, because we drilled in straight, we should be able to put just a straight plug in there. On those, we'll just push the cellulose in. We'll take our foam gun and we'll just squirt in here. Let that, go ahead and just work down with the foam gun, and then come back and just with our utility knife, we're going to then just cut that hole flush. That'll kind of seal the exterior sheathing. We'll take this, flip it down, and if we tape this now, basically we've made now that wall weather tight, and we're not going to get water leaking into our insulation. So it is important that we just don't leave these things like this and just put it over and put our clapboard or our siding back on. We potentially could have some issues with water intrusion. Okay, so we'll go ahead and pull off the back of this wall. Excellent. Okay, so when we're done, we can see that the cellulose has completely filled the cavities. So we put this other stud in here, like you'll find in walls. There's always extra things, or maybe there was a window in here at one time that got changed and we boarded it up. So when we're probing side to side, it also is a good idea not only to probe where that next stud is, but to probe back also. And that just assures you that you've gotten to the end of the cavity and there's nothing like a small one. Now sometimes you'll do that where you'll probe back and now you'll drill a hole, but if this were filled with, if it were 4 studs in a row, which sometimes you find in houses, but you're only going to know that now by drilling in, past that first stud there to see if there's another little cavity. Now this cavity is big enough to be able to fit a hose into. Sometimes you'll come up to a cavity, that's so close together we can't even get a smaller hose in there. We'll try to whenever we're able to do that, and typically if we get anything bigger than 1.5 inches, we'll be able to snake that in. A couple things that we see. So the other thing is between 3 and 4 pound density, the cellulose will take on a little bit of a different feel to it. Pull off this poly. Pull that back. Okay. So the density of that cellulose should feel, at 3.5 pounds, it'll feel kind of like a firm mattress. When we get to above that, so about right here where Zach was putting the hose in, we could see that the density actually feels a little harder here. So I can tell that that density is about 4 pounds per cubic foot there. And then elsewhere, it's nice and uniform, 3.5 pounds. I'm going to take the bottom of this out again just to demonstrate that it truly is self-supporting. Okay, so again, it's there, it's not going anywhere, a house can move, train can go by, the trucks can go by the outside, and that is not gonna fall down over time. So we got really good density, consistent density there. You can see it, filled all the way to the bottom. There's no gaps or voids in here. Now, when we're talking about material drop-off from the hose, if we're blowing fiberglass, what we have to remember is that the fiberglass fibers have less weight and won't flow as far, so it won't, what will happen if we're blowing fiberglass is that density drop-off is a lot more severe. So if we blew the same wall with the same hose, with fiberglass at the appropriate density, and those densities typically are about 2 pounds per cubic foot, what you're going to find with fiberglass is a greater density drop-off, so it'll be really light even just away from where that hose is, even laterally in there. And from the testing that we've done, actually with Building Science Corporation up in Canada, we found that the air leakage reduction with dense packed cellulose is much more significant than if we use the fiberglass, even at the those 2 pound densities there. So you're going to get better air leakage reductions with dense pack than you will typically with fiberglass, unless you're tubing these walls multiple times to basically compensate for that extra density drop off. So basically what you would need to do with that to get the same effect is you need to send your hose down to the corner here, send your hose down to the corner there, and go ahead and insulate basically the same way up top. So you're, instead of coming down once, you'd be going down at least twice, and the same with up on top. All right. Okay, so in terms of, so we do quite a number of mobile homes up in this area, and we find that there's basically 2 types of floor systems on there. Sometimes the floor joists are basically going across the home, and then less often, but we run into them where they're basically running the length of the home. So when we're doing that, sometimes it makes sense, particularly on the length, we use rigid tubes in there in order to get the hose, you know, all the way to the center here. A lot of times we're coming in from both sides on this. This one, a lot of times you can actually either do it from under, well, all of these you could do from either underneath or through the ends of them. And if we're doing it from the ends, then we're going to use a rigid tube. So here's a 2-inch, and the key here is thin wall PVC. So if you use regular PVC, it generates enough static between the walls that you're going to get shocked severely. I've seen with some of the big air pump truck mounted machines where you get sparks that are over a foot long, sound like a whip cracking, and will literally leave guys just laying on the ground for a while. So you want to avoid standard PVC. So the thin wall means there's less static buildup. You will get a little static buildup on here. And let's talk a little bit about static. So we have to remember with static that basically as we're blowing, we're generating static from the hose, and that's getting imparted into our body or ourselves. And then typically when we're touching something, so either the remote or maybe a piece of metal, we're going to ground ourselves out. That's when we're going to get the static. So in terms of static, there's a couple things we can do. One is if we can have our remote kind of on our belt, if the static is real bad, if we can touch this, either hold on to it or touch it more frequently, we're going to be discharging smaller amounts. The longer we let that static build up before we touch that, the worse it's going to be. So wearing thick gloves and things like that a lot of times doesn't get rid of the static. It just means that eventually the static's going to build up so much that it's going to shock through your clothing, and certain areas there maybe where it wouldn't be quite so pleasant to have a big shock going through. In terms of hoses and things, that Tiger Flex hose, I didn't mention this before, we'll talk about it now. So we've gone to these Tiger Flex hoses. So Tiger Flex is the brand name. These are plastic braided rubber hoses. So what that means is they're very, very kink resistant. We really can't kink these hoses, and yet they're flexible. So in the summertime, we want a hose with a good flex. We find that this Tiger Flex hose with the green braid actually works great in the summertime. So I kind of think of it as grass out there, green to get the green hose. In the winter, we'll want a more flexible hose, because as the temperature drops down, these hoses become less flexible. And if we have this hose in the winter time, it's going to make it more difficult to kind of bend it up in there, particularly when the temperatures drop below 20 degrees, is where we're going to notice it more often. But again, rather than the straight, clear kind of milk hoses that we had used before, these are going to be very resistant to kinking, because you kink and all of a sudden now you've clogged the hose. So we want to avoid doing that. Back to the big rigid tube here. Nice thing about this is it's lightweight. So we're going to actually be able to connect several of these together. So we can actually drill our holes at the end here and now start feeding that one tube in here. Now with they have the connectors that connect these two together. We're going to tape those up. Sometimes we'll put a screw through it so we don't lose that. And now we'll be able to now take that hose, and sometimes we can actually feed it at least halfway, and sometimes all the way to the end if we're lucky and not hitting other things in there. Turn on our machine, and we'll be able to go ahead and dense pack all the way back out. Sometimes also, if the attic is large enough, sometimes we'll use these rigid hoses, tubes in the attic as well, if we can make sure that we'll be able to pull it out all the way. That way we know exactly where the end of the hose is. The trouble with a less rigid hose is it could be, moving around a little bit in that cavity. So if we're doing something like this, or even something like this, we should be able to figure out what the distance between, so how wide basically these floor joists are, what the spacing is, and we know the length now of the home that we're insulating, and we can now figure out how many bags per bay. So basically what we'll do is we'll set the machine, we'll go ahead and stick it in here, we'll insulate that first one, and on paper This bay should take 8 bags of cellulose. When we get done, we're going to check, see how many bags we did. And again, from that, then we're going to, whether it's more or less. So if it's less than 8 bags, we're going to know that the density was not high enough. So therefore, we're going to now reset the machine and insert that tube back in to bring it up. If we've used more than 8 bags, let's say 9 bags or 10 bags, we'll know that density was a little bit more. We might make some adjustments to the machine, open that feed gate up a little bit more to get the density to where we want it, and now calibrate it so that we're getting the proper amount in here. But this way we can now, before we insulate the entire building, we can know that everything is kind of dialed in. And the same with this, we can calculate the area of these, and if we need to, we can, maybe do 2 bays here, and we know the number of bags. Did we achieve it? If not, do we need to make some adjustments on the machine? So that way, that with using that bag count, we can get things really dialed in, and we know now that we're putting it at the proper density, and we're never going to have separation. We're never going to have settling within those cavities. So another way, if static is really bad, which some of the agencies use, are these basically static reducing bracelet, basically. So you're going to wear this around your wrist, and now you're going to clip this to something typically that's grounded, but sometimes you can even find like a nail or something will provide some pretty good relief. And as long as you're not working too far from that, you're now not going to build up that static. You're constantly discharging it, so you're not going to get shocked when you're touching things. So this can be helpful. Some folks have used graphite in the past, but if you ever look at the SD safety data sheet on the graphite, you probably will never use graphite again. It's not good to be really inhaling that stuff. It's really not great for you. But that's the way they'd use it in the past. We've kind of gone to using hoses and things like that are kind of less sensitive to static and just don't build it up like the regular PVC is important there. All right, while we're standing in front of the wall here, we'll talk a little bit about hole plugs. So again, 2 9/16 inch plug. That one maybe slightly small, but that could be used on that hole that we just had drilled straight in. The beveled edge, unfortunately, makes it so this plug doesn't fit as well. We could theoretically put it in and then foam around it or caulk around it. You probably can still do it with that one there. The figure 8, it's probably not worth doing too much with these regular plugs here because you need to do some cutting, and that's just going to take too long. Push the cellulose in, get your foam gun, foam it, let it dry, clip it off. 3-inch hole. We could use a 3-inch plug, which I have here. So again, if it's a little with that big hog bit, it's a little loose, but we could put that in and we could caulk around that, make that work if you wanted to go that way. Some people use those foam plugs, and then there's this kind of plug as well, which has kind of a little bit of a lip on it. If you were so inclined, you could put some caulk around that and put that in as well. So there's just a couple different ways of plugging that wall after we're done insulating it. Okay, so let's talk about where we have multiple story buildings and we have floor systems between the floors. So if we have and that'll happen when we have a balloon frame or even platform framing. We'll have some sort of, in balloon framing, that cavity is going to be in that floor system. So it's going to be connected in, but even platform framing, we can have that same thing. So if we have our house here, we have our floor joist going across. Okay. So in these buildings, even platform framing, what I find, at least in the Northeast here, is when we turn the blower door on in the winter time and we look up at that ceiling on the first floor or the floor on the second floor, we're going to see a lot of cold air intrusion through this outside edge. The band or the rim joist is going to be letting a lot of air come in there. And in some buildings, it's so substantial that if we do a good job with everything else, the walls, the roof, everything else, that leaky floor system will not allow us to kind of reduce the air leakage to a point where we're going to be happy and the homeowners are going to be comfortable and we're going to save a lot of energy. So doing this really makes sense in a lot of different buildings. So the question is, how do you insulate that? We could insulate the entire floor system. We could fill it completely up with cellulose, but we're going to use quite a lot of material doing that. And really what we'd like to do is just keep the air from the outside from getting inside that floor system. So what we're going to do is we're going to use a system that we call the improved bag and blow system, where we're going to use either a grain bag or a maybe kind of a onion type bag, or a bag that grapefruit's in it. And I find that this size actually works pretty well. Even though it looks like it's really large, we need it big enough so it can expand between basically these floor joists here and seal the edges. So we're going to go ahead and I'll show you the demonstration of that. But basically, in the simplified version, what we're going to need to do is we're going to need to block off this one, this bay here. Need to block that off. We're going to need to block it off on this side also. So we're going up on our ladder, removing the siding from this area, drilling our hole, and here we're drilling, typically that, maybe 2 9/16 inch hole. We're then going to use maybe a shorter length of tubing sometimes, and sometimes I'll even take a piece of this rigid tube, cut this off so it's 18 inches, 2 feet long, hook our hose to that. It's just convenient when we're up on a ladder not to be having the big hose out there. And then we have to remember on these two end joists here, we actually have to go ahead and fill that entire bay in order to block this off. So when we're done, we're going to have it insulated on all 4 sides in order for that to be effective. And we'll go ahead and do some in our prop here so you can kind of see how we're doing it and what the improved part of the improved bag and blow actually is. Okay, so for the improved bag and blow, we're going to pull the grain bag over the hose. What we'd like to do is try to set the bag so that when it inflates, it's going to inflate, fill the whole cavity. So we're going to try to orient it in so it can do that. So here we go, putting the bag in. Grain bags are pretty tough, so rarely do you ever push the hose through it. Okay, great. So Zach also is leaving enough grain bag on the outside so he has something to hold on to. If he didn't do that and turn the hose, the material on, the bag could shoot now to the edge of the cavity there. So now he's got that secured. He's going to go ahead and turn on the machine. We can see the bag inflating. It's important to have the bag of the right size. So if we use a garbage bag or a regular plastic bag for this, what's going to happen is it's going to inflate and then it's going to pop because we got too much air going in it. The grain bag, again, is going to allow that air relief through while containing the cellulose insulation. And the material now is dense packing in here. In the old days, we would just fill the bag and then move on to the next bay. The improved version of this means that when we're done, we're actually going to push the bag in and dense pack from the bag to the outside. And by doing that, we now are able to take care of any air leakage now around the edges that in the old days, we didn't take care of.
Check the hopper.
Okay, now he's using the hose in his hands to kind of push that bag in place. Just a couple inches just to give us some room there now to basically dense pack the rest of that cavity.
Pass me one of those onion sacks.
Oh, here we go.
Thank you.
Some folks will use the onion bags. They look like they have some pretty big openings, but they do contain the insulation pretty well. The thing is with these, you can puncture through them pretty easily because of the material, but they can work if you can get bigger ones. This one's a little too small to be able to fit most of the floor joist spacing that we're dealing with. Okay, so he's pushed the bag in now. Now he's just going to basically dense pack between the bag and the outside. We can see now that the cellulose is how it's filling now basically the rest of that cavity. Now, as you can see, it's important to get the density good in that bag initially, because if you don't, the bag is just going to slide further in here. But now when we're done, now we have no air spaces here, so any leakage now is contained in the, we've contained any air leakage. Great. And as we can see in here, we had a grain bag, but because of the floor joist spacing, it was wide enough where one bag didn't do it. So in this particular one, what we would do in the future, if we didn't have a larger bag, is we would use two bags. We put one in, basically on one side and inflate it, and then push the other one in and on the other side, and then again push those in with the hose, and then dense pack outside to complete the job. But yeah, so it's important that these bags be big enough so that they can expand, and this size seems to work pretty well for that. So after we've done insulating our let's say our wall system, it's important that we do our quality control, quality insurance. So part of that was, again, the bag count. We know how big the wall is, we know how thick it is, so we can determine the number of bags we should have used. Also, the infrared is just really helpful in quickly being able to determine whether we get things right. Infrared cameras have come down a whole lot from when I started over 25 years ago, where the cost of the infrared was several times more than a vehicle, and these days for a couple $100 you can get a usable infrared to do this. So with infrared, it's important that we have the temperature difference. We can use the infrared in the winter time, we can use it in the summertime. We just have to make sure we have enough temperature difference. We also have to remember when we're doing infrareds on the exterior, on our buildings, that we take into account what the sun is doing. If the sun is shining on this part of the building, it can reverse that infrared image. So it's important that we know that before we start going in, because we can kind of be a little fooled by that sometimes. So we're just going to make sure that what we're looking at is just really consistent. The nice thing about the cellulose is the performance of it is really consistent. So it'll be just very uniform color from top to bottom, and if we see any areas that we missed or areas where there's light density, it'll be really apparent in the infrared, knowing that we have to come back and do some additional work on that. So again, probing, we're going to do our probing, we're going to do our bag count, we're going to do an infrared, and if we do all those things, we're going to know that we got a rock solid job, and we're going to get the energy savings that we had planned on that. So let's talk a little bit about the differences between cellulose and fiberglass for doing these things, because in theory we can use either of these to do walls and floors and things like that. So a little bit about the differences between the two. So first, the material. Cellulose is typically made from either newspaper, or we're using a lot of cardboard in our material, just because there's a lot more boxes being shipped for people to get things these days. So that's wood fiber. The thing that's nice about wood fiber is it's hygroscopic, which means kind of like that paper towel. So if we have a paper towel and we have it on the table and we pour a little water onto it and we watch it, what we're going to notice is that higher concentration of moisture is going to slowly spread out. And if we watched it long enough, it would actually spread out evenly throughout that paper towel in that case. The same thing would happen with the cellulose. And this, actually, some people think that's a disadvantage, but actually it's an advantage, because what it does is it allows the cellulose to be more resistant to little amounts of water creating problems. Fiberglass, on the other hand, is hydrophobic, which means it wants nothing to do with moisture, but that means that moisture basically can move right through the material, hits a cold surface, condenses, and because it's hydrophobic, it wants nothing to do with that moisture. It can then cause problems where you get excessive moisture rotting things out. So this is also why we can use cellulose without vapor barriers, because what happens is in the wintertime you get that outward diffusion of moisture, diffusional moisture flow. The cellulose, because it's hygroscopic, basically now is spreading that moisture. So we don't get moisture accumulating now against that exterior sheathing and causing problems. With fiberglass, that would not happen. If you had the same moisture going through a cellulose wall and the fiberglass wall, what's going to happen with the fiberglass is that same moisture is going to go out, but it's going to hit the exterior sheathing, condense. You got liquid water out there, and now because it's hydrophobic, that liquid water is just going to stay out there until you have, problems with your exterior sheathing rotting away or mold or something like that going on. So in terms of moisture, as much as that hydrophobic properties is protective to the insulation, hygroscopic properties tend to be more protective to the building assembly in general. So it's protecting those materials that are surrounding the insulation itself. So this is spun from glass. This takes quite a lot of energy. So if you looked at the amount of energy per pound, you'd be putting 12,000 BTUs per pound to manufacture the fiberglass and about 750 BTUs per pound for the cellulose. So a lot less manufactured energy. Also, because it's wood fiber, we're actually putting carbon into the building and storing it that way. So if you're concerned about global warming or global climate change and things like that, and carbon dioxide levels in the atmosphere, the cellulose actually is now incorporating that carbon into the building for the life of the building, and basically keeping it from now decomposing and basically coming into the atmosphere. In terms of just the usefulness of blowing these things, fiberglass has improved. The old stuff was pretty bad to work with. They certainly softened it down. But in terms of protection and things like that, these fiberglass, newer fiberglass products, the way they've increased the R value on them is they've decreased the fiber diameter. And the trouble with those smaller fiber diameters is it means that those are going to go deeper into your body. So these are going to lodge deeper than the cellulose. You'd want. There's one other thing I guess I want to kind of add to that if I could. Let me get my sense here what I was going to say. Okay. So there have been concerns in the past about, what if the roof is leaky, or what if a pipe breaks in the floor system on a mobile home? Isn't it better to have the fiberglass in there? The reality is, if you have a roof leak or you have a plumbing leak, whatever material is in there, you're going to need to get out of there. And the cellulose is going to be more resistant, where you could have smaller leaks and not have an issue. Now, granted, if a tree punches a hole through the roof and you have bulk water going in there, you're going to have problems, no matter what materials you have. So roof leaks, plumbing leaks, basically, in my mind, whatever's in there is going to need to come out. The cellulose is going to be able to respond to smaller leaks without issues. We work in the weatherization programs. We're going into buildings that sometimes the roof systems. Again, if the roof is leaking, we're going to want to install neither of these products. We're going to want to fix the roof leak before we go up there. But if there is a little bit of a leak, again, the cellulose is going to do a better job of helping to spread that moisture out and reducing the damage from that from happening. You know, in the 11 years I was in the weatherization program, I can't remember any of them except one time when we had a call back of, you know, you insulated my building and now I have a roof leak, you got to come and take it out. And that was one where a tree literally had punched a big hole through and a lot of water had come in. So it's either the buildings that we had been working on didn't have roof leaks, or that the cellulose was able to manage these little bit of leaks without any particular issue.